Hi everyone, welcome again. Our next speaker is Xihui Xie. She's from University of Pittsburgh. All of you know already. So Xihui, you can start.
Okay, I'm going to share the screen. All right, so everyone can see the screen.
Xihui, is there any sound problem?
Can you hear me?
I can hear you, but there is like a buzz.
I'm using my earphone, so maybe let me try connect again. Is it better now?
Yeah, it's perfect now.
Okay. All right, so hello everyone. Okay, so here's my topic today. So it's the new ideas for penalty method, and this is also my thesis topic. All right, so today we mainly have two main topics. The first one is a double adaptive penalty method for the Navier-Stokes equation. So this is we using the penalty method and also control the penalty parameter in time. That is to say, in each time step, we want to pick an optimal penalty parameter. The second topic is on adaptive grad-div parameter in penalty method. So this one, we try to control. We try to control the penalty parameter in space. So that is to say, in each element, the triangulation element, we want to pick the penalty parameter differently. And last, we will talk about some possible future work. So the first topic, doubly adaptive penalty method. Here we consider the incompressible Navier-Stokes equation. It is time dependent, and we compose with this incompressible condition div u equal to 0. We apply the penalty method. That is by replacing div u equal to 0 by div u plus epsilon p equal to 0. So here epsilon is called the penalty parameter. It's a small number, usually far less than 1. We use a screw symmetry nonlinear term, and eliminating the pressure in the equation, we can get this following penalized Navier-Stokes equation. So this equation you see doesn't contain the pressure, so it makes this equation much easier to solve than the previous coupled system. All right. So this penalty method is very efficient, right, and also costs less memory. Right. So the question is, there's many papers already started the penalty method, and they found that the solution is sensitive to the choice of epsilon. And also in this paper, we do a little test. So this is the plot of error at final step with constant time step versus a different value of penalty parameter. So we see for different time step, constant time step, the left-hand side is dt equal to 0.05, the right-hand side dt is 0.02. So for different time step, the penalty method has the different optimal penalty parameter. So that's to say, the choice of epsilon depends on many conditions. So the question is, can we automatically adapt the penalty parameter epsilon for each time step? Our idea in this paper is very simple. So it is we pick the penalty parameter based on the residue div u norm at each time step. All right. Okay, so here we are first did the numerical analysis. So we are using the backward Euler in this paper. All right. So first result is the stability of this constant time step backward Euler. All right, so U star, so here U star representing the linear extrapolation of U at a time t(n+1). So U star is different depend on which method using. if it's constant time step, then U star is a UN. And if it's a variable, then we'll have a different representation for U star. So we see this method is stable. But apart from study the stability of the velocity, we also need the stability for this acceleration. And in the acceleration, this UT term is very important. So by using the penalty, we have div u equal to negative epsilon p. And using the LBB if soup condition, we have this left-hand side, the pressure norm is bounded by this right-hand side. So the right-hand side, the first one is the problem data, and the last two, these two are bounded from the previous stability bounds. So next, we need to have a bound for this UT term, because currently we are considering the stability for the backward order. So next, we are considering the discrete norm of UT. And for simplicity, here we only consider the linear Stokes problem without the u dot grad u, that nonlinear term. So the result we are getting from the linear Stokes problem for controlling the epsilon is also very important to control the epsilon for the Navier-Stokes equation. So this is a zero stability result for UT. So we have, if we increasing epsilon or if we decrease according to this relation for some alpha larger than 0, then we will have this stability bound. So I need to mention that if throughout the whole time, the epsilon is only increasing, then we will have the unconditional stability bounds. But if we decrease the epsilon, we cannot decrease too much, and we only have the zero stability bound. So that says unconditional stability holds when increasing epsilon arbitrarily, and stability holds when decreasing epsilon, provided epsilon is not decreased too fast. And next, this is a test confirming that the epsilon condition from the stability is very necessary. So this is a numerical test with exact solution. All right. So for the Navier-Stokes equation. Okay. So here we have two plots. The left-hand side is the epsilon value, and the right-hand side is the norm of UT. I need to mention a little bit what is each colored curve look like. So here we use a backward order plus the time filter. So with the time filter, we can easily adapt the time step and also to make it to be first order, second order, and the variable order. So here in this picture, the blue represents the first order method, and red one is second order, and the yellow one is variable order. So this is the result of variable time step, variable epsilon method. So we see that at the right-hand side, this plot, there are many spikes of the UT norm, and the spike happened exactly at the time when we decrease epsilon too much. Right. So this confers up condition from the previous stability bound. So we cannot decrease epsilon too fast. The next test is a test for a flow problem. So this is a flow between offset circles, right? And here in this test, we want to compare two different estimators. The first estimator is naturally we have this div u norm, and the second estimator is this div u norm over the grad u norm. So this relative residual is independent of the size of u, and also it has the benefit of being non-dimensional. Right. So to compare with these two estimators, the blue curve here we are using is the result from the coupled system. And also this coupled system, we add with the grad-div stabilization, also with finer mesh and a smaller time step. So here I can say this blue curve is more closer to the real situation. Right, so we see that both estimators with adaptive penalty method, they control the div u better than the coupled system. So we see this yellow and red curve. this is a DView norm, has smaller value than this coupled system. And also the evolution of the pressure, this is pressure, and the lift and the drag, these two are lift and drag, behave similarly for both the estimators. So currently we cannot draw a conclusion which estimator is better, so the future study will be needed. So here is a conclusion. So we present the stability bound for both velocity acceleration, and also in the paper we present the error analysis. And this paper main results show that we could increase epsilon arbitrarily, but when decrease, we cannot decrease too fast. And the paper also presents their both constant and variable time step algorithm. And also the numerical test shows that decreasing epsilon too fast will result in the catastrophic growth in the UT norm. Okay. Move on to the second project. So this is we adapt the penalty parameter in space. This is kind of a new idea. So we begin with the simplest setting, which is the steady state Stokes problem. We still use the penalty method, replace dvu equal to 0 by dvu plus epsilon p equal to 0. Eliminating the pressure, we have this penalized Stokes problem, right? So for the rest of this presentation, I'm denoting this triangle as a mesh element so that we have the integral over the whole domain omega can be written as a sum over all elements. And also the area and volume of a region is denoted by this notation. The idea is very similar to their penalty method for the Navier-Stokes problem. We want to monitor the residue, the dvu, to control the error in each element. So while the local residue, this local dvu norm is large, we pick epsilon to be small. So a little analysis. So we take the variational form of the Stokes problem and also take the L2 inner product with UH. So we have this following equation. And also here we are considering epsilon is different on each element. So we write the second term as follows. So this implies when we globally halving or doubling epsilon, it will have a doubles the dvu norm squared, right? So our goal in the project is to control the dvu norm such that it's less than some local tolerance. And in practice, we want this dvu norm squared to be approximate equal to 1/2 this tau squared. And let's rewrite this equation. So for the left-hand side, we write this as a sum over all elements. And for this right-hand side tau squared, we can write as this as follows. So we get this following equation. And here, this leading to the local tolerance. The local tau is defined to be 1/2 tau squared over the volume of whole domain multiplied by the volume of each element. All right, so that implies that for each element, we want to control the dvu norm such that it's approximate equal to this local tolerance. So this is how we exactly do. So on each triangle, each element, we have our epsilon old value, and we solve for the velocity. We calculate the ratio as follows. It's equal to the local tau over the dvu, local dvu norm. And then we adjust the epsilon by using epsilon new equal to r, the ratio multiplied by the epsilon old. And then we resolve until for each element, the local tolerance is satisfied. So in practice, when we do the error analysis, we start with the epsilon old to be equal to 1, and we only adjust once. So the first step is therefore epsilon equal to this local tau over this dvu squared. So this is our choice of epsilon in our formulation. So this is a first option, which is I call the Elementwise penalty method. All right, so that is for each element, they share one common penalty parameter. And by this option, that gives the nonlinear grad-div term in this right-hand side, this variational form. The second option is we consider in another way, is that we consider epsilon is different at each point. Right? So that gives our epsilon to be equal to this local tau over the dvu norm at each point squared. And this also gives a nonlinear grad-div term in this following right-hand side. So in our error analysis, we only did the error analysis for option 2, as if you notice the right-hand side, this structure share the same structure as a P-Laplacian. So that way it has the strong monotonicity and the local Lipschitz continuity property. So in the error analysis, we are going to use these two lemmas. So before the error analysis for pointwise penalty, I'm going to mention the stability result for both pointwise penalty and the Elementwise penalty. We see that the grad-u norm and also the dvu norm is bounded. Right? So here's the result, the error analysis result for pointwise penalty. So we assume our velocity space satisfies these two approximation properties, and then we have the numerical error of pointwise penalty. So I want to mention that the second term of the left-hand side and the first term of the right-hand side, these two share the same structure. And also, if we have this velocity space has the d-free subspace, then this left-hand side, this first term will vanish. So that way we will have a better approximation result. Okay, and next I'm introducing the numerical test. So for the first numerical test, so in the test, I'm using the Elementwise penalty method. And this test is tested on the steady state Stokes problem with an exact solution. And these two following plots are the local dvu norm of local dvu norm of the both coupled system and also the Elementwise penalty problem. So we see the left-hand side, the coupled system. The scale is approximate 10 to the negative 5. And the right-hand side is our Elementwise penalty Stokes problem. So the scale is approximate 10 to the negative 6. So the Elementwise penalty has smaller dvu value. And next is the detailed result with different mesh points on each side. So previously, we have 40 mesh points on each side. So next we have 10, 20, 40. So we see that actually if we have fewer mesh points on each side, the advantage of Elementwise penalty is more clear. So we see that this penalty has smaller dvu value, and also the error of the penalty method is approximate the same as a coupled system. Okay, next is the numerical test. So here we extend this Elementwise penalty to a time-dependent Navier-Stokes equation. And this equation is tested on a 2D flow problem. And here is what the domain look like. So it's called the flow around the cylinder. So this test, so the problem mainly is how can we adapt the epsilon. So here we use the previous dvu value to control the epsilon for the next time step. So here we have two options. So for the first option we have is we just did this adjustment like once. So we do not do the repetition. So the second option is after we do this step, we check if the local tolerance is satisfied. If it's not satisfied, then we need to adjust the epsilon again. So here I call it the without repeat and the repeat the step. So that is corresponding the right-hand side is dvu norm. The blue one is without repeat, and the red one is repeat the step. So we see actually both the d-view norm is well controlled, but when we repeat the step, the result will have smaller d-view value. But the cost is when we repeat the step, it still needs more calculation time. So left-hand side, this is a result from without repeating this step. So we see this is a magnitude of the velocity field and the vortex shedding off the back of this cylinder. All right, so we can say that the element-wise penalty method can predict the flow problem accurately. Here is a small conclusion. So in the paper, we derived the element-wise penalty and also the point-wise penalty for the Stokes problem, and prove the stability bounds for both, and also error analysis for point-wise penalty. So the numerical tests show that element-wise penalty on Stokes problem have smaller d-view value compared to the coupled system. And then finally, we extend the element-wise penalty to the Navier-Stokes equation. And we adjust their epsilon using the previous d-view value. And also this algorithm could predict the flow accurately. And here are some future possible directions. So we can also do the error analysis of element-wise penalty on the Stokes problem. And also, we also want to study the locally adaptive penalty for the unsteady nonlinear Navier-Stokes equation. So our final goal is to combine the results from project 1 and project 2 so that we could do the adaptive penalty method for the Navier-Stokes equation and make the penalty parameter adapted like both in time and in space. Okay, so here are some references for all their time filter used and also their experiments I used. Okay, so thank you, everyone. Any questions?
Thank you for the talk, Xihui.
Thank you.